I want to show you how we can start making code in Unity that runs as fast as ECS, but that's built on game objects, which is exactly what we're seeing here. We have 100,000 objects, 90,000 of these cubes that are moving up and down, and then we have 10,000 of these city buildings. This project is available on GitHub. All right, now I'm going to show you how I did this, and I'm going to then explain in a little bit of detail how to start thinking about this down to the assembly level. Now, I also want to point out that this presentation is following the Unite presentation. I was going to be speaking with Richard Fine, and I ended up not being able to make it, so he presented the whole thing, and I did this as a few video clips. That goes into a little bit more of the lower level, like the unsafe C#, the pointers, so you can really start getting even deeper with the memory. I'm going to try to give you a little bit more towards the DOD side, the data-oriented design. Anyway, let's start off. The game objects, everyone's familiar with game objects who works with Unity. That one, you drag a cube into the scene, you got a cube floating there in the sky. And you want to give it gravity, you drop on a rigid body component and suddenly it falls out of the sky. That's game objects. It's a what you see is what you get editor. It's straightforward, it's easy. However, with that ease of use comes an expense. And so they ended up coming out with DOTS, data-oriented tech stack. That includes things like native arrays, that includes ECS, that includes burst compiler. One of the big things you use is arrays of structures. And you're not allowed to use things like classes or strings. What I'm going to show you today is data-oriented design. Data-oriented tech stack is an implementation of DOD. Let's go over some rules. I'll try to cover the basics of this, and then I'm going to go into more details. So I want you to realize that RAM is slow when it's random. However, what's the R mean in RAM? Random. Random access memory. RAM is slow when you start to access it out of order, but there are mechanisms on the computer that will allow you to do it faster. Class order is random. When you instantiate a class, even if you're instantiating a bunch of them into an array, all you're getting there is pointers to the actual class object that sits somewhere else in memory that you don't get to control. That means that it's random, which leaves us with slow RAM. So we need to use unmanaged struct arrays. It's just like floats, bytes, integers. It doesn't include arrays, classes, or strings. And the last thing is that we need to draw in batches. I want you to get out of the idea that you've got a game object that has a renderer, and that renderer is going to draw that one game object. That's expensive. And let's go into our demonstration again. Let's try game object. So here's our one game object. It's just a simple cube that floats up and down. It's the basic default cube. The only changes I made is I turned off lighting because I'm not trying to measure lighting performance. I'm trying to measure the performance of instantiation and how well it keeps its frame rate up from how much data I'm cycling. On here, I have this prefab grid and I can click +1K. There, it added 1,000. Technically, it didn't add 1,000. It made sure I was adding at least 1,000 more. To create 1,024 prefabs, it took 241 milliseconds. 241 milliseconds is a quarter of a second. That's expensive. Let's expand this again. Add another 1,000. 2,000 took 471, almost half a second. 4,000 prefabs took almost a second. Most of the time when we use prefabs, we only instantiate a handful of them. I'm going to change this to 10,000. So that to make 10,000 took between 2.5 to 3 seconds. These are just basic cubes. And then let's go draw a simple grid. Okay, now I just clicked this one, turned it on, and you'll notice there's no children it has. But yet look at all these objects. And look at our frame rate. It's like 300 FPS. 10,000 prefabs took 2,746 milliseconds. This took 1. That is the difference between game objects and ECS. But we can do the same numbers. Let me show you the code. All right, so all that you need to know is that we have an array of matrix 4s. What is a matrix 4? Effectively, it just lets you store a position, a rotation, and a scale. It's your transform object. Except these are just a 4x4 array of floats. But remember, a quaternion is 4 floats. A vector 3, like the position and the scale, is 3 floats. What we are going to do is build a batch of them, where I create a new array of these based on a total area size. Every single one of them is going to get a different position, a different rotation, and a different scale. So when we're adding them to the batch, we're calling matrix 4x4 TRS, which means translation, rotation, scale, or position, rotation, scale. Now we have an array of our transform. And finally, this is the function that does it. Graphics.drawMesh instanced. In this case, we are drawing a single mesh, a single material, and an array of matrices. So that mesh with that material is going to be drawn at however many locations. So when you're looking at something like this, a whole bunch of cubes, that's really easy. I can give them all their own scale, their own rotation, their own size. And here I've got 10,000 of them. This one's kind of cheating. There's no movement inside of it. Let's add some movement here. I'm going to draw water. Let's start out with, in this case, 90,000 cubes, because why not? I can add another 10,000. We'll go up to 131,000. So 10K didn't exactly work out, but all right. So we've got 131,000 cubes that it added, and it took it 12 milliseconds. These, again, are just basic default cubes, except they don't exist in objects anywhere inside the hierarchy. How does this wave pattern actually work? I'm not concerned with the algorithm for it, just one key piece of information about it. We loop through every grid element and we grab a batch. So now we have our batch. Next, we're going to manipulate the positions of that batch. And then we're going to draw. We're going to do the same draw mesh instance command where we pass in the mesh, the material, and the batch. So now we're going to change this. We want to change the data. Now inside of here, all I'm doing is I'm taking data and using more data from the same item in the array. I just pulled out a matrix. There it is. I pulled it out of the batch. And now I'm manipulating the values inside of that with other values from that same object. This means that when I access the memory, I'm saying, hey, give me this item out of the batch. Then the CPU can read it and say, I went out to memory and I grabbed it for you. Now you can use it. 100 to 400 CPU cycles have passed. Now it goes around to the next batch index and it grabs the next batch. And it says, okay, we've moved forward 64 bytes, but we've only done that once. I've only changed the memory one time. And then it comes back to the third time and it says, we're reading this same spot, this same array, and we keep jumping farther ahead in RAM. And it's the same amount. I'm going to go make another request right now that I'll run in the background while the rest of the math is working. That means that before we get to the next line where it's asking for the next index, the prefetcher has already asked the cache RAM to go load it from the RAM. And it now means that our memory costs might not cost us anything. If it takes us 400 CPU cycles to finish the math equation, then we will get that RAM call for free. Now, the city in here, this has another complexity. Each batch can only have one mesh and one material. So first off, I have the material down here. This is using a technique where they use the same material across each one of the meshes. This is an artist technique. Remember, when you're trying to improve the performance of a game, this is not just a programmer's playground. This is your designers. This is your artists. This is everyone involved in it, making decisions, as long as they're educated on it, making decisions that help improve the performance. So one mesh, we don't need to load up more materials. Anyway, so we've got a whole bunch of meshes here and it's drawing them. Now let's go into the actual code for it. In this one, I also have a two-dimensional array of batches, but the two-dimensional array of batches, every index of it relates to a different one of the meshes that we have in here. Here, I have 18 meshes. Then I'm going to have 18 as the first number in the batch. That way, every single item gets its own type. Now, there's one more that I want to show you. Water 2 has a unique difference from Draw Water. So Draw Water 2, first off, you see it's got a different math equation that's building it up. But in this case, I have two separate arrays that are controlling it. So let me go into the code for a second and I'll show you this. We have our batch index, and inside of here, we also have a distance. We have a batch array and a distance array. The distance array is just the floats. We stored the information based on how far it is from the center. And so our math equation on that can be a lot lighter. Whatever the equation is, the point on this one is that instead of going through memory in a single line, in a single streamline where I say, hey, give me the first batch, then give me the second batch, then give me the third one, I'm now going, hey, give me batch index 0, then give me distances index 0, then give me batch index 1, then distances index 1. How on earth is it going to be able to determine the leaps in memory like that? The systems need to access multiple arrays. When we're jumping between array 1 and array 2, doesn't it go from A0 to B1? Let's draw this. Over here, I've got A0. So the first time we get through here, we're going to access this. It accesses A0. Then it jumps over and it accesses B0. And then B0 comes over and accesses, or after that, it accesses A1. And then from A1, it jumps to B1. How is any system going to understand that we are accessing these points in memory in sequence? Because when you get down to the assembly code, it doesn't actually understand that you're looking at an array. In fact, it doesn't even need to be looking at an array. I want to start explaining a little bit about the assembly and the CPU side. You don't technically need to know this stuff, just understand that the arrays, it can track which array is doing which. But I wanted to go a little bit deeper so that you understand this at a lower, more intrinsic level and can really pull out of it what's happening here, why it's slower, why it's faster, how it does its memory. So you're not making guesses. Or at least that you're making less guesses, because most all of this is guesses, and then you have to test it and make sure that your guesses make sense. The CPU has two sets of memory. The first part has data. We also have a separate section that is on the instructions. So it pulls in a section of RAM that has your instructions in it. I took a little bit of liberty to not make this straightforward assembly just to make it a little easier to understand. It is this equation right here. So we are going for I equals 0 to 1024. I didn't do the initial setup up here where we start up with I equals 0, but we are looping through the code. And then each time we're going to add B to A. The first one is that we have a get command. The get command gets the value from memory, which R9, if it starts with R, it means it's a register. RAX is a register, R9 is a register, RBX is a register. A register just means this is a spot where I hold a value on the actual CPU, not in cache RAM. This is the CPU where it can now operate instructions directly against it. Beforehand, it was just memory. Now it's active. R9 right now is starting out at 0. R9 equals I equals 0. That's what it is right now. So we're getting the first value from the array, and we're saying, hey, give us this array. And technically what it's saying is, hey, give us the next pointer here. And whatever memory is there, stuff it into RAX. So at this point, we're getting the value of A. And we're storing it into RAX so that we can use it. Next, we're getting the value of B, because we're also using B here. And that puts it into the value of RBX. The fact that I have A going to RAX and B going to RBX doesn't matter. Next, I'm going to add them, RAX and RBX. Now, what happens is the values get combined together into RAX. There is no equal sign. You're at a very low level. The CPU just thinks of these as one thing it's going to do at any point in time. One operation, one instruction. So it's adding these values. And so RAX gets the combined value of both. Then we take that and we set that value. RAX is now getting set back into here. It actually uses a push and pop commands. They aren't exactly the same, but they're close enough. We have now added the two values together and put them back into memory. Next, we're going to increment R9, which just means add 1 to whatever the value of R9 is. That's our plus I plus plus. Next, we're going to do a compare, CMP. We compare 1024, this one, with R9. But what does that do? That doesn't do anything. Well, remember, we're thinking one piece of data at a time. It does the comparisons and then it stores the comparison somewhere else. Greater than, equal, less than. And next we go to the next line where we say jump. So this is our loop where we jump back to the beginning. And our loop is JL, and it takes us to address 80A4. This one, 80A4. So once we've done the loop, it brings us right back up to the top. But wait, this is JL. JL means jump if less than. If our comparer came up, if it was less than, it stored that value into a flag that marked it's less than. So we are going to jump back if it's less than, and otherwise it just continues on to the next instruction line where we're done with the loop and it's moving on in the code. Somewhere down here, going through farther in your lines. That's assembly. Tiny little instructions, little things happening one at a time. But your computer is able to do billions of them in a second. We have an instruction that says, get the value of A. That's right there. That happens at 80C4. Oh, I've got a mistake in there. 80C4. That's a mistake. That should be A. Yes, that happened at 80A4. Yes, right here. It's telling it what instruction it happened at. And then the next time it comes around, when we ask for A, and then the next time we get to that same line, it's asking for 160. So right now, at this point, we know that we have jumped forward 64 bytes, but that doesn't mean anything. Who knows where we were before in our code? But at this point, once we get up to that third one, where we have gone to the third item in the array, and now it notes, I did 64 ahead from the A address, from this offset, 2 times in a row now. That means that the next one that they're going to ask for is probably going to be 64 bytes ahead again. It actually keeps a little table of data. From that information, it can determine if it can start reading ahead. Now, it only stores a handful of these. The processor decides how it controls and dictates that. But the idea is that as long as you're not doing too much and your instructions haven't been flushed completely out of memory, because there's only so much memory to hold your program, but as long as it hasn't been that long, then these registers and this history is still being held. So if you're doing an array, you want to do small sets of instructions against that array, as opposed to I loop through one item of an array and then I do 800 instructions to it, and then I come back to it to the next index. By that point, the table that's actually storing information might no longer have this address listed on it and have zero concept of reading ahead. Of course, at that point, you've been jumping through memory so much that reading that stuff ahead might not add any benefit anyway. So that's the point. When you look at ECS code, you see ECS code as I've got an array of simple structures of data, and I keep asking for them in sequence. As long as you're doing that in your own code, you can just write your own arrays of structures and do that. You could still just take a section of your existing code and start modifying it so it works with this strategy. All right, I'll talk to you later. I hope you found this useful.